All right. So, hello, everybody. Welcome to this virtual visit of the CMS experiment. My name's Lael. I grew up in northern Illinois, actually about an hour away from Fermilab. And then I went to undergrad at the University of Alabama and then moved back up north. I'm currently a PhD student at the University of Wisconsin-Madison. And about 6 months ago, I moved from the US to France to do my research here at CERN. And it's been really great so far. So I'm excited to share this great experiment and hope you're excited.
And I'm Pieter. I'm a research scientist also at the University of Wisconsin-Madison. I'm originally from Belgium, but I've worked for the US for 15 of the last 20 years, always at CERN. I've always been based here for different US institutes. So
Very good. So I'm actually going to be heading down to the CMS cavern, so I'm going to get ready. You go ahead.
Okay. Okay, so welcome everybody. So today we're going to visit the CMS experiment. So you guys have probably already gotten a little bit of an explanation, but I think also, yeah. So I also see, you have the picture also available, of actually the whole accelerator. So you can actually see, okay, you have this big ass accelerator, which is 27 kilometers. It goes, and, in 4 different spots, you'll have collisions that are basically happening. So you have the Atlas experiment, which is our main competitor, and then CMS completely at the other side. And then there's 2 other dedicated experiments for looking at specific physics more clearly. But, we and Atlas, we are, the main, what we call general purpose experiments. So what that means is that we will try to find all kinds of physics which might be possible. So whether you're talking, whether you're talking about looking for a Higgs boson, or you're thinking about looking at other kinds of particles heavy ion collisions, things like that, we're able to do all of that. Not all of it as good as some of the dedicated experiments, but we can do all of it. And so CMS, the one that you'll see today, is actually the small one, because CMS stands for the compact muon solenoid. So we're actually quite compact compared to our main competitor Atlas, because we are around 8 times smaller in volume. So, you will see that it still makes a very big detector. We'll still have 15 diameter detector, which is 21 meters long, but it is considerably smaller than the others. A big chunk of our detector will be our muon detectors. That's why we have also the M of the muon in the detector. So also that, again, you will see at the moment they're downstairs that, most of the volume is filled by that.
I think Lael has something for you.
Okay. Lael?
Hear me?
Hello.
Yeah, we can.
All right. You guys hear me okay? Okay. So here we are at the first step to enter CMS, the access point. And CMS, we take safety very seriously. So what I have here is a very important piece of protective equipment called the dosimeter. So what this device does, it measures the amount of radiation I've absorbed working in certain parts of CERN. And also it has a device, a chip inside of it that stores all my information, all my credentials. And part of that information is, okay, what safety courses have I completed and what areas of CMS do I have the authorization to go into? And fortunately, I do have authorization to enter here. So we're going to go through this spaceship door. So I take my dosimeter, scan it. Nice click. I'm going to go in. And typically, this also scans your retina. Right now, it's disabled, but we'll see that more in the future. And now Noemi is also going to go through. I mean, this part's great. I really do think it feels like in Star Wars, they got those tunnels on the spaceship, and it feels like you're going through that, at least to me.
And you can see that Noemi made a mistake going in because she has to go out again. That happens as well.
Yeah. A little finicky door, but it gets the job done. All right, we're going through. Hopefully now. Very good. Okay. Onwards to CMS. So now we're in the room where we can access the elevator. So all sorts of doors around. We have this guidebook. So if you ever visit CMS, you can put your name down, become part of CMS history. And now we're going to press this button to go down through CMS. I hope you're all excited. It's already here. During this elevator ride, our signal might cut out. So Peter, I think it's a good time. If you want to keep talking, maybe see if the audience has any questions, and we'll meet you down there.
Yeah.
2?
Okay,
3.
So Lael is going to
No,
-3, which will be to minus
very good.
97 meters actually underground. So you will actually see it go down, but at some point it will basically stop.
I think very soon.
Yeah, it's
Right
because
now.
it's because we're losing network for a little bit. So you will also have that, like one thing which is very particular about this elevator is that it's actually, like it's one of those places where we have to take the elevator to be safe, actually, to go underground. So, like you have too much of a risk if people try to take these stairs up and go 100 meters above, because then, like somebody could get into trouble and could block actually the evacuation. So as a result, you always have to take this elevator where there's like overpressure air being pushed into. And so it doesn't have any risk for fire hazards. It doesn't have any risk for gas coming into there. So it's always the safest area. And so it's a little bit of an exception we have with other places. Do you think Lael will come back now, or do you think I should?
Well, I will see when he is back.
Okay.
That's a very peculiar thing. On the way down, we lose connection. On the way up, we don't.
Yeah.
That's the roaming between the two countries, France and Switzerland. We got a question. Is it built across the border of France and Switzerland? Yes.
Yes. I mean, you can actually see it on the picture, which is, I think, is it still on the screen?
Well, if you want,
yeah, just put it back.
Lael is
I mean, if you see the picture, then you can actually see this white dotted line. That's the border. So actually, the LSC crosses. The LSC crosses 4 times with it. Like it crosses the border here, 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 and here.
We don't need to pay taxes for the process.
No, exactly. But
actually, this is, as far as I know, this is an agreement of the two countries.
Okay. But we basically are here on the French side at this moment.
Yep.
Like, like CMS is fully French. Let's put it like that. But,
Vive la France.
Yeah. So, Lael, are you back or not really?
I think he is
hello.
halfway here.
Yeah, you're back. Okay, go
can you hear
ahead.
me?
Yeah.
Okay,
go
very
ahead.
good. So now we're down here, 100 meters of rock above us. There's excitement in the air, and we're going to enter into the CMS experimental cavern. So we have a second point of safety. Again, takes very seriously. So, speaking of safety, the only thing we want to be colliding down here is particles. Not heads, not feet. So, second safety check. Make sure you have all the right equipment. Make sure you have the authorization. So again, here I'm going to scan my dosimeter, and then it's going to look at my retinas to verify that I'm actually the one carrying my dosimeter. So let's head in. Scan it. Door's going to open. I got to take my glasses off. And then I align my eyes with this device. Oh, it told me to get out.
It's usually the opposite. I have to.
You can actually put it upwards, right, Lael, if you want.
Oh, so yeah.
You don't have to bend over.
Okay, let's try this one more time. I'm just going to go down. Okay, it scanned me. I'm authorized. Okay. Hello. So I'm on the other side, and Noemi is also going to make her way through the access control. Okay, scan the dosimeter. Now we're going to line up the eyeballs once again. Let's see. Very good, we made it. So, quick note. If any of you, are thinking about coming to steal my dosimeter and my eyeballs to get into CMS, I appreciate the enthusiasm, but there are easier ways to get in. But that's good. Okay, so now
Lael, we got a question actually, which is like, there is a lot of radiation at this moment in the tunnel. So it's saying like there isn't much radiation at this moment in the tunnels, right? During the shutdown. Right. So could you elaborate?
Yeah, so of course, when the Large Hadron Collider is running, we have these protons coming and colliding. and that releases a lot of sort of stray radiation into the experimental environment. And some of that does sort of also get captured in the surrounding material. But right now, we're in a shutdown period. The safety team has made sure all the radiation has cleared out. If there's ever any situation where it was not safe to enter, we would never be able to enter in the first place. So right now, totally safe. Everything's being cleared, so that's good. And as Pieter said, the IHC is not running right now, so we are good to enter. Okay, let's open this door. It's very heavy. And here we are. Wow, this is the moment we've all been waiting for. So I guess we want to kind of do it in reverse. Do we want to go? Okay, okay. So right now we're on the ground floor called X1, and this is our first view of the beautiful CMS detector. So CMS, as we'll sort of learn more about during this tour, is made up of different slices. And right now, CMS is closed. All the slices are squished together. And what we see in front of us is this big block of shielding. Just we mentioned, radiation can come out of the collision points, so we want to make sure as much that is contained as possible and gets absorbed by this. Pieter, do you know what material this is made of? This big red block here?
It's just steel, I think so, right?
Let's go.
Red is steel.
Yeah, the red is just steel. Right?
But what red you see is a steel casing and concrete behind.
Mm-hmm.
I see. Very cool. So as we're walking along the detector, hopefully our signal stays intact here. We'll show more of this a little in detail as we get to the upper levels, but you can already see a lot of the infrastructure, a lot of the pipes and connections in the experimental cavern. They're preparing for opening, so we see, oh yeah, a lot of work is going on.
Normally it looks more tidy.
Yeah.
This is what you see as Lael and Noemi told. This is the preparation for opening exactly this part of the detector, and obviously that requires quite a few equipment to be brought down.
Yeah.
Normally we are much more tidy.
Yeah. And actually, one thing I think you can also see in between, which I always think is something to pay attention to, is how tidy the cables are done. I'm always amazed by the cabling job that was done on CMS, and it's because it was necessary, but it's like, it's something which is really impressive. Okay.
Oh yeah.
One of the biggest problem today.
Yeah. I know.
Wow. So this is actually an amazing sight. I've never seen the LHC beam pipe this open before, but you can see that that line there. This is where the protons come in, traveling near the speed of light, and collide inside the detector. And that's the Large Hadron Collider right there. Just that piece of metal. Really, really amazing. And we create this gigantic detector, and you can see above us the shaft that they used to lower down all the slices of CMS when it was originally built. And there it is. And just a very brief explanation of, we have this, how heavy is this detector, Pieter? Like 14,000 tons?
14
it
and
is,
a half.
Yeah, 14 and a
let's
half.
just say
14 and a half.
you can't really pull it, unless, I mean, Pieter's pretty strong, but definitely not me. So what we have here is this very unique system. You see these orange pads here. I think what we call these compression pads, where essentially they push compressed air down, and it almost lets this massive detector float like a air hockey puck on the air. And then they use this winch system with these heavy-duty steel cables to pull that slice of CMS forward, and that's how we can open it up and do all the upgrades, all the work that we need to do. Really, really amazing technology. So we can also show here, hopefully, some of the residual magnetic field of CMS. I can already feel it. We have some paper clips. Okay, let's see. Wow. So Pieter, maybe you want to explain what's going on here. Why are these not falling? Did I break gravity down here? What's going on?
Well, I think the magnet is off, but everything gets magnetized after enough time, in this object. So, this is just the residual magnetization that we still have of the whole detector, and it just gives you a feeling for how strong the magnetic field has to be normally, because now you have to think this is with the magnet off that you see this. When the magnet is on, you can do the same game with like heavy duty tools. I mean, and you can put them in the direction of the magnetic field without any problem.
Surely, when the magnet is on, we don't play this game with the paper clips,
Yeah,
because they might fly through
exactly.
across the room, and they might create shorts. Instead, we use, as Peter said, an M19 wrench that sticks there quite heavily.
Yeah.
Well, we'll never fall. We'll never fly through the room.
Yeah,
That's an important thing.
yeah,
Extremely spectacular.
yeah, yeah.
Okay, so I think we can head up to a higher level, and as we walk, maybe it'd be a good time if there's any questions or anything else you guys want to say upstairs. Let's go.
I don't see any questions at
No,
this
me
moment.
neither. Me neither. If you have any questions, please don't hesitate to ask
Oh, yeah.
through the Q&A.
But, you know, like, yeah, I think Lael also showed the hole where we lowered the whole of CMS, right? And it's one of those interesting things as well, because, you know, like one of the problems we had with CMS was that we couldn't really build the detector underground immediately. So we had to build everything above ground. And this was partly to do, I mean, it was partly planned, but it had to do with groundwater, which took longer to build the thing.
Also, don't forget, we had an accelerator before
exactly,
here,
that as well.
Large Electron-Positron Collider with its tunnel. And this tunnel, at the place where Lael is now, had to be enlarged.
Yeah.
Okay.
And this took several years.
You know, and so as a result, you know, we built everything above ground, and then we lowered it. And so actually, if you go above ground, then you use again these feet, because, you know, like the crane that we built, it was much easier to have a crane which only went one-dimensionally up and down instead of going also sideways. And so we actually have a concrete slab, which is 1.5 meters large, so almost as high as me, which can close off this whole, like, you know, top hole. And then you can basically go into that, and, you know, like, you put the detector on there, you hooked it in, you remove the floor again, and it started lowering. I think Zoltan will show a picture now, actually, from one of the lowering.
There.
Yep.
But so for me, you know, like, I was a young PhD student the first time we lowered one of those pieces, and I was extremely excited because I was like, I'm gonna go there, I'm gonna watch this because it's gonna be so fun. After an hour, I left because, you know, they had moved like 3 or 4 meters, because, you know, the big problem is that if this thing starts wiggling, you can never get it under control. So it was a very, very careful operation.
I think it took 8 hours.
Yeah, like it took around 8 hours for every piece to be lowered. So, you know, like, it went extremely slow. And, you know, like, it was just one of those things which was one of those big challenges which we actually had on the construction. So yeah, like, you know, there you see as well how it's basically coming down on the picture. And, you know, if you go to the previous picture here, I think you could also see how the concrete slab was actually there. This one, not the next one. I think we can see here you can see this is the hole which can actually close off, right? This is
exactly. This is on the surface.
This is the hole.
We have a very nice pithead cover.
Yeah,
we can just slide in.
Yeah, exactly.
Indeed, that could withstand the weight of this piece that you see on the picture, which was 2,200 tons itself. So you might imagine that we sometimes organize parties on this pit.
Yeah, we've had a CMS party on there more than once.
What is your favorite particle?
Oh, there's also a question about how much it costed in the chat.
Yeah, exactly. And also, how does the detector work to detect signal? I think you want to dive into it.
Or maybe Lael wants to talk for a little bit. I mean, Lael?
Before that, do we have any favorite
particle? Sorry. Oh, we're back.
Yeah.
Well, I will say quick answer to that. My favorite particle. So I'll go number 1, electron, because it powers all modern electronics, and we're made of a lot of electrons, so I feel special connection with the electron. But muon's number 2, because that's also what I work on with Pieter. We love muons.
I think we all agree that the muons make our money.
Yeah, exactly.
Oh yeah.
They pay our salary.
Oh, yeah.
So
thank you, muons. Really good.
Well, so probably the smallest supersymmetric particle.
Yeah.
that would be pretty nice.
That would be my favorite. Yeah.
And I think just checking on where we're at. So right now we are up at one of the highest levels, directly facing CMS along the Large Hadron Collider beam pipe. And this is an absolutely incredible view of the LHC and the detector here. I mean, hopefully you can kind of get a glimpse of the sort of center of CMS from this angle. At least in person, we have a pretty good view of it, and it's really spectacular. So I think from here, we're going to head up actually to the top of CMS, which is a very, very exclusive view. So it's going to be good. Here, maybe if you could remind me some of the other questions, we can all, I guess, answer them as we walk up at the top.
There was a question about how much it actually costed.
Oh, I think
you know, or otherwise I can answer.
I'm going to say around $8 to $10 billion.
No, that was much cheaper.
Well, that's the whole,
okay.
But the accelerator and everything, maybe, and all the experiments.
Actually, what we have to make clear here, that all these things that you see around are unique.
Yeah.
Therefore, the price tag is very relative.
Yeah.
I don't know what we should count as a price. The material cost, which is fairly low, or should we count the expertise that we put in that's priceless?
Yeah.
For everything else, you have the
no, but you know, like if you look at CMS alone, so like CMS alone, the material cost is around $500 million.
Yep.
I mean, that's the rough price of CMS alone. Then the accelerator is a few more billion, all the other experiments as well.
Actually, we had a very cheap accelerator.
Yeah.
We didn't need to dig out the hole.
It was
that's the most expensive, you believe or not.
No, but the big problem is that it's very hard to count also the person hours which go into it and the salaries of that, because, you know, like we rely on a lot of PhD and master students, which, you know, like are paid in all kinds of different ways, but we don't necessarily pay them for our project. So, you know, like all that money doesn't come through CERN and stuff. It's done by the university. So it's very hard to estimate.
We had something like 10,000 people in total. In this journey so far.
Wow.
If we would count everybody's salary, it would be enormous.
Yeah. Okay, wow. Lael, what are you showing us?
So right now we are on top of the greatest science experiment ever built. Right here below us is one of the two experiments that discovered the Higgs boson. I mean, we are really sitting on top of a tremendous piece of the history of science. And I think also something that really inspires me about CMS, I mean, this is what can happen when we come together, we build something in a collaborative way. I mean, look at this. This is what we can create. And it is, hopefully you agree, absolutely amazing. I will give an abrupt transition from that very inspiring speech to mention these big red things, which is what happens if the experiment catches on fire. So what happens with these? Only. The last resort. So these will spray down foam in case there's what, I guess, Zoltan, you probably know better, some sort of uncontrollable fire in the experiment. But hopefully that's not happened.
Maybe also at the end of the LHC, we can have a big foam party there.
if we all are here, of course, we will see. So indeed, this is the last resort, as we mentioned. We have many other sophisticated smoke killer or flame killer equipment. But if it would happen, I hope never will happen, but if it would happen that we get such a fire, then we don't need to preserve the detector anymore, but the underground gallery, then these would be operated. Before their operation, that would be a very hard decision to be made. I think there will be only one or two people who are overpowered.
Oh yeah. Maybe a couple more things we can show up here. One is the crane system. So that big yellow contraption. So they use to move very heavy equipment down here. We also have, again, the what do you call it? The shaft above us where they lowered down the slices of CMS. And it's actually open right now. You can see some sunlight up top. More directly in front of us, you can see a lot of the wiring that connects all the different components of CMS.
Oh, wait, we got a question about the color schemes.
Oh yeah, that's a great question.
If the colors are chosen on purpose, could you tell us something about?
Well, I know for the wires that we have in these trays, I believe that the blue ones are to power low voltage electronic components, and the red ones are to power high voltage electronic components that need a lot of power. And then, yeah. And this is all for the system that Peter and I work on, the muon detection subsystems. I think then the copper wires are to supply gas systems. So any component that requires gas to function is supplied through these copper lines. And you can see it's very sophisticated. All the other colors, for example, why is this green? Why is the crane yellow? That I don't know if there's a good answer to.
That's probably
Always.
Yeah, the yellow crane is yellow everywhere at CERN. But as Noemi says in the background, the various subdetectors have different colors for their data and low voltage.
Yeah.
You can't see it because the detector is closed now. Maybe you see some white. That's the hadron calorimeter. But I think from X1, from the ground floor, you would see more cable types. This is our liquid helium vessel, a 5 cubic meter one, where we pour helium on our magnet. We have a superconductive magnet. We have the biggest one, what concerns its physical size, not the strength. We have, yeah, exactly.
I think it's also almost the biggest one on stored energy, right? I mean,
the stored energy, and also about about the size in general scale, not only among the superconductive magnets, but the strength. We are just only 3.8 Tesla field. There are much more energetic magnets around, but much smaller volume.
But I don't know where it's true, Zoltan, but I was told last time by somebody that the energy stored was roughly the one of a Boeing 747 taking off.
This is what I used to say. Yeah. Exactly. The kinetic energy.
Yeah.
So you might imagine that if such a magnet decides not to be a superconductive anymore, you have to pump the stored energy somehow out, unless you would do the same thing as a Boeing 747 crash landing. We don't really want to have it 100 meters underground. Therefore, we have sophisticated electronics and solutions to mitigate this issue. This is what I used to say, that this is called quench in physics notation. And what I used to say, how I used to describe it, this is one of the sacred secrets of our religion. How you mitigate the quench. That's why it is very hard to build a superconductive magnet. But we are not going to talk about it today.
Peter, can I drink the helium in that tank? What would happen?
I think you would freeze.
Probably not.
Yeah.
So, you know what is the temperature in the helium? If that is actually today we don't have helium in the tanks, but you know how cold it is.
Maybe Lael knows how much it is in Fahrenheit, because I don't know in Fahrenheit.
No, unfortunately not. I think it's like negative. Is it around -2 Kelvin, or is that too low?
It's 4 Kelvin. Yeah.
It's 4.2 Kelvin.
Oh yeah, negative Kelvin.
Yeah.
I got to go back to school.
Yeah, exactly.
Interesting. I'm really interested in that. Cool.
Also, we've made it to the other side of CMS. There's the other piece of the LHC beam pipe, and you got a pretty cool angle here, showing a bit of a cross section, split in half with a lot of the shielding around it. That's pretty amazing.
Yeah, like, so normally when you have a beam, there's a lot of particles flying around it, and so you get a lot of junk with a beam, and so this is why we put this orange shielding basically around it, protected.
This takes us to the next question. Although the detector is turned off for now, is it still connected to the particle source? No. This is incompatible with the works what we are doing now. We are very much picky on this. We do not allow any people in the cavern when the particle beam is on. Even though the radiation level where Lael is now would not be lethal. We are not in a nuclear power plant, of course, but this is higher than the legal limits that are allowed in not only Europe. I think probably the US levels are the same. That is, we are really, really on this. If anybody would enter the cavern during the particle beam, it would immediately shut down the full 27 kilometers ring. And of course, you would hear about it in the news the next day.
It wouldn't be a weasel.
I don't know if
No.
I don't know if you guys can see. Sorry, we're at one of the slices of CMS. I don't know how well it shows up on camera, but we have the barrel to the right here, and then to the left is where we start this end cap that goes on to that middle part at the end there. Pretty amazing.
Yeah, so the detector closes as much as possible because, like you want to avoid having too much dead area, because every dead area gives you like fake signals for like, invisible particles. And we're interested in invisible particles because if we want to discover something like dark matter, invisible particles are like, one of the main things that we have to be able to see. And we can only see them by actually looking at whether we have a conservation of energy and momentum inside the detector. If we don't, then we know that something left undetected. And so if something leaves the detector undetected, it might mean that it's a really undetectable particle, which is the most exciting case. But it can also mean that it went into an area where there's just no detector or where the detector is not working. So these are the kind of things that we have to understand actually to really be able to see.
We try to minimize. The first one we try to observe.
Yeah, exactly.
As the lightest supersymmetric particle would be undetectable. At the same time, I put on the schema of the detector. So you might see that we have 5 barrel wheels like bread slices and 3+3 end cap plates. Therefore, we, as Pieter said, we try to cover completely the 4 pi solid angle around the interaction point, as much as it is possible.
So Lael, one of the questions was also how we detect signals and how we detect particles. So maybe we leave this picture on and you can actually, if you give a little bit of explanation. Okay, fine. So Lael, do you want to explain a little bit about the detector, or do you want us to do it, about how the detector works and what are the different slices or everything we have?
Yeah, so sorry, Noemi, I want to look at this picture. So we see here, so unfortunately we can't quite see it in person right now, but different particles can come out of the proton-proton collisions in the LHC. So, for example, sorry, I got to look at the picture. Everything starts off.
Let's start with this picture.
Sure.
This one. So I think this is what you told, that during a particle interaction, a huge amount of debris is produced.
Yeah. So these are not just very clean collisions. You get these massive sprays. And in the middle of this photo, you can see the tracks coming out. And that's measured by the innermost layer of CMS, the silicone tracker. But of course, we want to know more about the particles than just their initial trajectory in that very small space. So next is the electromagnetic calorimeter. So this is able to measure the energy of particles like electrons and photons with a very high resolution. But those aren't very good for stopping and measuring the energy of heavier particles, what are called hadrons. So beyond the electromagnetic calorimeter, we have this next layer called the hadron calorimeter. So charged particles like, I'm trying to think of examples. I think pions are a big example of
even protons and neutrons, right?
Everything that contains
protons, neutrons.
Yeah, that all gets stopped.
Oh yeah. So all that hopefully gets absorbed in the hadron calorimeter. So we get a measure of their both where they were going through the tracker and combine that with their energy measured in the hadron calorimeter. But then we have these magnificent particles that make it through all of that. They just fly right through, and those are our favorite muons. So what those go through, they go through the tracker, electromagnetic calorimeter, hadron calorimeter, leaving, I think, small deposits. But then really where they shine is this outer piece the muon detectors. And that's actually that middle acronym in the name CMS, so compact muon solenoid. Because you can see most of the things that you see on this tour are this gigantic muon system, which is able to track these muons with a very, very high precision. You see all these tracks are bending, and that's thanks to the superconducting solenoid in the middle, which bends particles both on the inside and then the residual magnetic field on the outside. So we have this full map, and each piece is like it's like an organ, right? CMS is a body, and each piece does its part. And you put all this information together, and that's how you can make these discoveries like the Higgs boson by using all these in collaboration. And I think, Zoltan, you know, is this a Higgs event?
This is a Higgs candidate event. Yeah.
Higgs candidate.
It was sold as.
You never know 100% sure where it's a Higgs event or not, right? We just know it's a candidate. I mean, like in the end, we're always dealing with statistics. That stuff looks a lot like it, but you can't be 100% sure because, you know, like we never record. We don't see the Higgs boson itself. We see its decay products. So as a result, like, you know, we only have a certain probability that it's a Higgs event. And this is one which is very likely to be a Higgs event, but, you know, like we can't be 100% sure.
And of course, all you back home, the future of science. Of course, you guys, if you're interested, can go into this field, experimental particle physics, analyze all this data, which will have much, much more data come with the high luminosity LHC. So it's really a great time, I would say, to get into the field. Hopefully you guys join me. It's a great time. Okay.
Why do we need higher luminosity?
Well, it's like Pieter said, oh yeah. So many of the work we do, it's not like you just look at one specific proton collision. You have to search for very rare processes, and you have to have a lot of statistics. I don't know if this is a good analogy, but these proton collisions, each time, it's almost like a slot machine. You know, a huge range of things can happen, and some of them are very, very rare, but very, very interesting. So in order to properly understand it and separate it from background events, like, oh, this could mimic this thing, you have to take a ton of data and analyze it all properly. So the high luminosity LHC is going to be able to capture much, much more of that data. And it's going to be great. Hopefully that answers the question.
Perfect. Yeah.
Very good. So as we're walking, we can see here up close the individual slices of CMS. And you can see there's a ton going on here. All different cables, everything squished there compactly. It's really amazing how we're able to do all this. Maybe Pieter, if you want to explain what happened here. Why did someone come and steal maybe one of the jealous other experiments, take all their stuff?
Yeah,
what's going on?
Zoltan has been working on it, I think.
Oh, well, I just sent in other people, but actually what we are doing now is the reconfiguration of the detector for this famous high luminosity LHC era. We are replacing quite a few detectors. Of course, there are electronics. We are actually what you are just showing is exactly what we three are working for, the gem detector. Therefore, this is a very, very complicated thing now. We are cutting cables, we are replacing cables, rebuilding the detector. This is the thing that is happening now is comparable only to the original building of our detector. You see cables cut there. Those cables are marked with the red tape. They are going to be removed, and some new cables are going to be laid down. Electronics that are already some of them are 20 years old. We are replacing with new models that can handle that enormous information that we are producing. Also, don't forget that we are blowing up the detector individual detection sensor number. Currently, we have 120 million of these, and we are going to go beyond 2 billion.
Yeah,
I let a little bit of time to digest.
Yeah, but it's like all of this is really like Lael is saying, just because, you know, like there's a likelihood to everything producing. I think for a Higgs boson, the likelihood, if I'm not mistaken, is roughly that 1 out of 10 billion collisions will give you.
I saw
Higgs boson.
a number from simulations that was corresponding the configuration of the LHC when we found the Higgs originally, and this was statistically 1 Higgs boson creation in every 3,000 billion proton-proton collisions.
Yeah, so even worse.
This is a very rare event. This we saw, but the reason why we didn't see anything of the dark matter or the supersymmetry is not only because it doesn't exist. It might doesn't exist as well, but it can also happen that these events are so rare that our detector was not able to see it. I know you are sitting somewhere around Fermilab. Fermilab had a very, very powerful accelerator called Tevatron in the 90s and the 2000s, and the Tevatron almost discovered the Higgs boson. The only reason it didn't see, or it couldn't confirm at 5 sigma, only 3.5, was the reason that their luminosity was not enough.
Yeah.
That's what we are trying to mitigate now.
So as we continue to look at the magnificent CMS detector, maybe are there any other questions or things from the Q&A?
Are there more questions?
We had one question concerning what are the typical byproducts of a Higgs event. I think we could talk about two different things. One is the very resembling events, the backgrounds, and also we could talk about the decay channels.
Yeah.
I let you are doing physics today, even not like I.
Yeah. No, like I think in general, so a Higgs boson can decay into many different options, but there's some which are easier for us to detect. I mean, like, okay, one of the reasons why the muons are basically in CMS and everything is because, we're extremely good in detecting muons because they're the only particles which reach these outermost layers, so they give a very clean signature. So actually the cleanest way that we could see a Higgs boson back in the past was basically looking for 4 muons. I mean, because if you have 4 muons, then you have an extremely clean signal actually of the Higgs boson, and it's the nicest thing you can do. There's some other possibilities as well. You could start looking at multiple light particles coming out. You can start looking for different types of quarks coming out, like the bottom quark, if you have 2 bottom quarks or things like that. There's also certain leptons that can decay in. You can play with all of it. But, like the ones where we really discovered the Higgs boson with was to look at the 4 muons as well as like, the 2 light particles. I mean, those are, the cleanest and nicest signatures. And so, like that's why we always love our muon system so much, because they actually, give us the cleanest signatures possibly from new physics.
But we could also talk about the amount of data.
Yeah.
I just mentioned the 120 million channels.
Yeah.
If you would have only 8 bits on each channel, we have more than 8. But as we get the collisions 40 million times per second. So if you all would multiply these, what I used to say that the bandwidth of God would not be enough to read out. Actually, today it is not perfectly true. When we built the detector originally, that was very, very much true. And if we could read it out, we would not be able to store it. If we would be able to store it, we would not be able to process it. We have to filter somehow.
Yeah.
And one of the solutions is the muon.
Yeah.
In the protons, that there are quite a lot of things. Besides the valence quarks, you have a lot of gluons, you have the sea of quarks, etc. But muons.
Yeah.
If you see muons coming out at the right time, right point from the collision point, then you can be sure that something interesting, as we call deeply inelastic scattering, happened.
Yeah, no, so the thing is in general, I think that, like protons are ugly objects because they're not elementary particles. There's a lot of junk in them. So when you collide them, there's a lot of junk possibly colliding, but none of it is, like he said, is a muon. And so muons usually give a very clean signature to basically say, hey, this event looks interesting. So one of the ways we select basically events is possibly asking like, oh, is there a high like momentum muon in there? Or maybe there's two muons with slightly lower momentum, but like something like that could that's probably already interesting because then there's something cool being produced. So it might not be a Higgs boson yet, but it might at least be another kind of like boson, which is already more rare to have, like the Z boson or something like that. So there are these possibilities. Lael, do you want to talk still more?
Yeah, I think along those lines, I just want to mention we're another one of the sort of shafts here, and hopefully on camera you can see this blinking light going up to the ceiling, and what that represents is data. I mean, of course, CMS isn't active right now, but data that comes from the cavern down here from CMS up to the surface where it's then distributed across the world. And Peter, like you were saying, this ties in with we have this whole triggering system, which I don't think we'll get into, but this whole way to pick out all these events that are interesting, that gets processed down here and then it gets sent up to the surface. And you can see sort of the scale of all that happening right here. It's pretty spectacular.
Yeah.
We also, do you guys, I think you know better than I do what this huge concrete block is. I think it's more shielding, right?
Yeah.
That's a plug. That's a plug.
The door.
Yeah.
The plug.
Yeah.
Wow.
It's just
Pretty amazing plug.
Yeah.
So obviously, when we are running, we wouldn't like to open the experimental cavern to the atmosphere.
Yeah.
Therefore, we make a hermetic sealing with that plug here, and we put a little bit less pressure in the cavern than the outside pressure. This also prevents the dust to escape from the experimental cavern.
Yeah.
If it would be activated accidentally, that would not leave the cavern. Just a fun fact, the accelerator is operating on an even lower pressure. So we don't even get the dust from the accelerator to the cavern.
Yeah. No, but when we're talking... Oh yeah, go ahead.
Oh, sorry. I was going to say, here's the entrance to the back rooms of CMS.
Yeah, just if you could just come out of the shade of the detector,
yeah,
to the nice shining Wi-Fi.
Yeah. So,
looks
but
like
you're breaking up.
Yeah.
So,
now it's getting better.
Yeah.
Yeah, exactly.
okay.
But we are 90% still.
Yeah.
It's not surprising. Actually grounded.
Yeah. But just to give you a bit of a number for what Zoltan was saying from the selection and stuff, like, we have 40 million times per second collisions. We only save around 1,000 per second to disk. So, like this is already a factor 40,000 that we actually save there. And when we do that, we still produce at the order of several petabytes of data per year, like, which means millions of gigabytes. I mean, so, like it's a huge amount of data. If we wouldn't do the selection, we would just create an absurd amount of data. I mean,
I have some nice pictures.
Zoltan has a picture.
Oh yeah, this one. The big data sizes.
Okay. I have never seen this picture, so I would have to. So Zoltan can explain.
So that's some estimation of the data produced, well, somewhere around 2023, and the bubble sizes show the size of the data. We are talking about the YouTube 260 petabyte per year.
Yeah.
The Amazon cloud was something like 500 exabyte.
Yeah.
And if we wouldn't have any filter on the LHC data, I don't even see, I'm too old.
Yeah, it says 40,000
kilo exabyte per year. And indeed, what we save as the LHC, what's the Monte Carlo, LHC real data in 2018 was 160 petabytes.
And it's now even gone up to 800 petabytes, right?
Yeah, exactly. Something like,
Yeah, so like, this for all the experiments together. So it's probably like, the 4 experiments. So CMS is around let's say 50 petabytes probably in 2018.
That's
I mean,
quite an amount of a
yeah,
data.
exactly.
I wouldn't like to read
So
it
it's
on paper.
50 million gigabytes a year. So
So I want to ask if maybe there's anything else you want to see here in the experimental cavern, or if we want to maybe go through the service cavern and take a look at some of that. What do you guys think?
I think you can start going to the service cavern.
Go service cavern?
Yeah.
Okay.
Oh, I
We'll make
think
our way up.
yeah, sure. I think we got one question, which was the light
Yep.
zipping up. Zoltan, you know very well what this light is. It's your little LEDs.
Yeah. Oh, you mean we are talking about that?
Yeah,
Sorry,
yeah.
that's not my mother tongue.
Yeah, this
yeah,
was
yeah, I happen to know the guy who made it. And actually, this was just an artistic view of the artistic representation of how the data comes out. Indeed, it has no connection with the data taking system. There were some urban legends about that it is somehow related to the trigger system, and it's nice to hear, but unfortunately, it's not true.
yeah. But I think it actually works out roughly. Like, some people say that it's connected to the bunches of protons, and it probably roughly works out to that.
That is a coincidence
Yeah.
between the individual bunches.
Yeah.
But again, the guy told me that this was the electronical maximum of this system operation. It couldn't be closer to each other.
Yeah. Somebody's asking how many collisions per hour would we produce when operational. So
okay, just make the math. 40 million per second.
Yeah, well, but it's even worse, right? Because every time we collide, we even have around 60 collisions at the same time, basically happening.
Have a nice picture.
Like, you can see here the picture that Zoltan will share now. Basically shows like, all these yellow points are individual collisions which actually happen.
This is the innermost part of the detector zoomed in. We have, as Pieter said, every yellow dots are individual proton-proton collisions. Overhanging part of that is a pool game, an elastic scattering. The proton disintegrates, therefore there's so many blue tracks. But no deep inelastic scattering happens.
No.
On this picture, we have one of them at least identified. You might see the red ray that comes out of one of them. That was probably a deeply inelastic scattering. That was a different particle. And that was identified.
But so you have to think that in general this happens because you're shooting bunches of 100 billion protons on 100 billion protons, like 40 million times a second. So if you shoot 100 billion protons on 100 billion protons, it's hard to just have one collision.
This is brutal.
So you end up with like, around 60 on average at this moment, which is the amount of collisions we're having.
And this we are going to crank up to 200.
Yeah.
I think.
Yeah, this is going to go to 200 roughly in the upgraded detector. But then you have to think this happens 40 million times a second, and then you can do all the math.
Yeah.
Lael, go ahead.
All right, so I think we're back. We are here in the service cavern, specifically a place called the counting room. So these are the power supply equipment for our magnificent muon detectors, the gas electron multipliers. I'm not sure exactly what to say specifically about them, but they look pretty awesome, I think. And right now you can see we're going through this transition phase as we head into the long shutdown of CMS, of the LHC.
This specific cable clutter will leave.
Yeah.
I don't want to touch.
And like Pieter was saying earlier, where's all this equipment gone? It's because, or I guess Zoltan, you were specifying, everything is being upgraded, being refurbished. But usually this is a lot more full, I would say.
So again, as I mentioned, we have 20 years old devices, especially for what concerns the data taking. Many of them is outdated. What we see here, this is the high voltage power systems of the DT chambers, the muon chambers. They are quite okay. They are not needed to be replaced, but this was a DAQ of something. I don't know by heart, definitely that must go. This part
PLCs.
is the safety system of the detector. Actually, this is going to go as well and replaced by a newer model. But you might imagine we have a baby that has been built only once. We don't want to burn it. We don't want to know how many smoke is in there to let it out. Indeed, therefore, we have to monitor very strictly all the working conditions, temperature, humidity, water, cooling systems, fire, whatever. And if anything happens that is risking the operation of the detector, we have to be able to shut down, to prevent the fire, to prevent the proliferation of the problems. That's the so-called detector safety system. And this electronics must be super safe. That's why we are using PLCs.
Texas.
You can see here one of our U.S. universities contributing. Looks like Texas A&M and UCLA. So that's a big part, I think, of the work we do in the U.S. is electronics on the detector. Here's one example of that. Peter, do you know actually what this is?
It's a trigger motherboard.
Trigger motherboard.
Yeah. So
CFAB.
Yeah.
Very amazing.
So actually, I think one of the questions ties in with this, where they're asking about the trigger systems and how this is filtered. So, like when we are trying to filter this data, this 40 million events to 1,000, we basically take 2 steps to it. Like the first step is that, we would start looking at a individual layer of the detector where we expect certain types of particles to be. For example, you could look at stuff like, okay, if you're interested in seeing whether there's signals in the muon detectors, you're just looking at the muon detectors to make your trigger. But you could also, for example, see okay, is there a big deposit in the calorimeters? Is there a lot of energy deposited there? Because then it might also be interesting. And so at first you do on one layer in the detector with fast electronics, you make a decision at the order of microseconds to basically decide it looks interesting or it doesn't. And this reduces us from 40 million to 100,000. After that, we send it to the computing farm, which is here upstairs. And there we can do more advanced algorithms. We can also combine the different layers. We have higher resolution.
There you have an enormous amount of time, 1 millisecond.
Then you have to the order of milliseconds to make another decision. And then you reduce it again from 100,000 to 1,000. I mean, then you can do very advanced machine learning algorithms. You can do all kinds of stuff there.
The first layer that you talked about that is implemented on the detector itself, we have something like 50-something trigger conditions. On the higher level trigger, we have hundreds.
Yeah.
But that's absolutely true. The first decision is the decision whether we read out of the data or not. This happens something like 100,000 times per second with the current configuration. And the reason why we gave this picture is that you might imagine this illustrates that for the muon, you don't need the data of all the, let's say, 250 barrel muon chambers. You need just the ones that are very close to each other. They can exchange data very efficiently, very quickly, and they can negotiate that, hey, guy, I saw something. Yeah, I saw something too. And the third one, oh, fine. Then let's instruct the detector to read it out. That's how the first level trigger works. As Pieter said, it's not only for the muons, but there are some other things, imbalance in energy deposit, whatever. I'm not the expert of this, but that's the way how we reduce.
And so you can have that, like it says, for example, oh, I don't see muon signals, so that's when it fails. But then I do have a big deposit of energy, so that it's then kept. And so we keep this in different buckets, actually, depending on where what it passes or doesn't.
One of my colleagues described it. The rule of the trigger system is to saying no, maybe, no, maybe.
Yeah.
Right. I think Lael arrived back on surface by now.
Yep, we sneaked our way back upstairs, and we're coming to meet you back in the control room.
Okay.
Oh, yeah. Let's see. So as we walk, I think very good explanation of the trigger system. If anything else you guys Want to discuss?
We lost him again, so
Yeah.
I will play you, Peter.
Play me, okay. And what should we discuss at this moment?
So
Still.
I think we've seen all the questions.
Yeah.
If there are any more questions.
Yeah, I think now it's probably best to just open up fully for questions, right? At
Yes,
this moment.
exactly. Yeah.
I think we've given a good overview and we can have a bit more discussion. And so, you know, feel free to ask anything you want.
Amanda, do you have any comments?
We're good. All right.
No, thank you very much for giving us the tour again this summer. I know it's a real highlight to be able to see this and see the experiment and hear from all of you. Extra bonus for having somebody that's a tour guide that grew up only an hour from here. So that's pretty awesome as well. But yeah, if there's any other questions, you know, put them in the Q&A from the audience. Maybe if you wanted to. Oh, and here's one.
Cool.
With the FCC upgrade,
No radiation.
how much changes to the data collecting systems are anticipated?
We're good.
Ooh.
Yeah, so actually for the FCC, which will be, you know, like for the people who don't know it, this will be a much bigger accelerator still. So it's another, like, you know, 3-4 times larger than our current accelerator. It will be almost 100 kilometers. Zoltan is going to try to bring up something. But so the general thing is that we need other detectors, because the data we will get, it will be very different, because the original FCC detector, FCC accelerator, will not be having protons colliding. It will collide, like, you know, electrons and positrons, which are positive electrons. And so as a result, the collisions will look very, very different. And so our current detectors are not optimized for that stuff. So we will build different detectors to be better able to study those. So there's a few, like, completely, you know, dedicated designs actually basically to do this. So here you can see actually the size of the FCC accelerator compared to.
First of all, this is the LHC. We
Yeah.
are sitting somewhere here at this moment, and that's what you might see. In the middle, you see the city of Geneva. This is supposed to go under the Lake Geneva. I think it's a very ambitious project. First, in the first working period, the so-called FCCEE is going to be built. Therefore, we are going to collide electrons and positrons, as far as I know, to measure precisely the Higgs parameters and try to open. That's my favorite sentence, to open the portal for the dark sector. So we are trying to discover the non-standard model or beyond standard model things. We are sure that there is something out there.
Yeah.
But at this moment we haven't seen. The Higgs is a very good stepping point for that, as we think today. Then at some point we are going to stop that detector, or stop that accelerator, and move on the so-called FCCHH somewhere around 2070.
Yeah.
That's a very important year. Well, actually 2071. I will turn to 100 then. So and that will be the ultimate machine in this century, to create something like 100 TeV proton-proton collisions, and hoping that we are going to see something.
No, I mean, one thing which might be interesting also for the people who are connected, I mean, you know, like if they're young people, is the fact that, you know, like when you work here, you actually do multiple tasks. Like, you know, partly you are building this experiment. I mean, and so that's where Lael and all of us actually work together. But at the same time, you're also trying to actually discover this physics. I mean, I spent 10 years looking for something called supersymmetry. I didn't find it, but, you know, like it's one of the things which you can do. I've also, like, you know, done some measurements of different processes just to see, you know, whether we can get some precise measurements and understand more from that. Lael at this moment is also working for his PhD thesis basically on a new measurement actually of, like, you know, something which exists in our standard model. So it's not, you know, some new physics, but it could still give us indications for, where new physics might be hiding. So it could be a very interesting thing like that. But so as a PhD student, you basically do both. You do like, you spend a big chunk of your time building something for the experiment because, like everybody has to contribute to make sure that we can take the proper data with the experiment. But at the same time, you spend time like, writing code, like understanding what comes out of this detector and really trying to really make some new physics discovery, hopefully, with it.
Oh, yeah.
We don't discover all the time.
Exactly.
Oh, yeah. Yeah, I mean, I just think even from personal like experience, it's been just really amazing working here. Let's see. I mean, I have friends back in Wisconsin, and they do theoretical physics, and they just sit at a desk all day and they write equations. And some people love that, but I think you come here, you get to really be hands-on, as Peter said, actually build detectors. I mean, see the detector in person, analyze the data for yourself. So I think if you're at all interested in particle physics, like it's really amazing.
We are all inclined. We love to do this way.
Oh yeah.
Yeah, I see we have another question actually.
Yeah, exactly. The question was: is the current LHC is a closed area like the Fermilab, or is it just open, exposed in the city?
So there's a difference here in the way that legally land is from somebody. Like in the US, you own the land until the center of the earth, right? I mean, that's why people who find oil under their land, they own this area. Here, it's not the case. And so as a result, the LSC can actually be built underground under everybody's houses.
But everybody has to agree on.
Yeah, but
I remember when we bought our apartment, ridiculous. We are living on the 4th floor, but we had to sign the document that we give access to the LHC, which is almost under our séjour.
Wow. Oh wow. Yeah. Okay, so my house might be just off that. I don't have to do it.
You are lucky,
but,
yeah.
But like it is possible. I mean, much easier here because like officially it's basically owned by the government, the principal, so they can more easily give permission to do this. But it's it's also one of the reasons why it's actually quite far underground because it makes it easier. Because like if it would be close to the surface, then probably more people would not want to sign the document that he's talking about. And like when it's 100 meters underground.
But also there are geological reasons.
Yeah, of course as well.
Before moving on the two other questions, one of them is very important in the scope of our discussions today. But I just would like to make another answer on this question, that we are exposed in the sense that we try to make very nice ties to the society around. We organize visits. We often discuss with them. The plans for the FCC is on a public hearing as well. So that are we just want to be part of the society around. We cannot be completely independent, even if we are 100 or even 400 meters below the surface. But let me just move on the next question. What are the opportunities for a US graduate students to work on-site at CERN? This is a very important question.
Lael, do you want to take it?
Wait, what are the opportunities for US graduates?
Yeah.
Oh yeah. Well, I can just overview answer. A lot. And honestly, you don't even have to be completely in physics to do work at CERN. We have, I think, from every area of STEM, people come here to do work. I mean, IT, the big one, I think, tons of stuff. But it really depends a lot on what university you're affiliated with. So for example, say you're a graduate student at the University of Wisconsin, certain professors will have certain projects they work on. And CMS, again, is composed of all these different pieces. So at Wisconsin, we work on the trigger system, those computational things that filter all the data. And then we also work on this part of the muon system, the GEM electron multiplier detectors. That's a mouth. I think pretty much you can look, different universities are affiliated with CMS, different universities are affiliated with Atlas, the different experiments at CERN. So it really depends on that. But what I've seen all across the board in the US is if you're an undergraduate student or a graduate student, if you want to get involved in it, there's a lot of opportunities.
Yeah, so I would say that probably you're talking about how many schools, like probably CMS and ETAS together is probably 80 schools or something, I would think, that have people at CERN. I mean, it's going to be something like that, 80 US, like, universities or something. So almost all of the, like big names you can think of, like, the top 2 or 3 tiers universities, like these have like people here, I think. So I mean, it's very common.
I would say it is very hard to escape.
Yeah.
Okay. On the other hand, I just would like to emphasize that any kind of engineers are needed, not only physicists. I think it's exceptional that we are all 3 physicists, but we do need electronic engineers, IT engineers, but we also need mechanical engineers. You just remember that these structures are very awkward. We do need top level mechanical engineers, and if you consider that we are working underground, the civil engineering is also needed. So we do need everybody. We need the souls.
Yeah. So actually, just today we had one of our, one of our colleagues leave, who was actually an electronics person who's going to do a master's in electronic engineering. So he just left actually earlier today. But so those people also come. It's a little bit less frequent, of course. I mean, I think, we have more physicists here than we have engineers, at least from the US. I mean, from Europe, it's a bit different because there's more people working for CERN. But, like from the US, it's like, universities have a limited amount of engineering positions, but they do exist. I mean, so we had somebody here who was first hired by UCLA and then by Notre Dame, who now went back to the US to get his master's degree, but he worked here for 2 years actually with us, basically, on the new electronics and how to control these new electronics in the optimal way. There's another question.
No, this question just leads us back to the to the city. Well, it doesn't matter. The question was about whether the new accelerator is going to go around the city of Geneva, whether it makes any problems or not. This will go so deep, something like 400 meters below the surface, that this will not make any problems with the properties, with the health, the environment, etc. The only question is the tunnel sections below the Lake Geneva. I expect huge disputes about it, not because it would make any threat on the society or the environment, but the plan to make motorway below the Lake Geneva on that side that would ease up the jams in Geneva was cancelled by the public. So definitely, I think this is the hardest point, but that's only my personal view. I'm 90% of the cases.
We will have to deal with the typical political things because like Switzerland has this specific political system where they have referenda about everything. So I would expect that here there will be a referendum whether this is allowed to be built or not. And so that will be the big question. So it won't be individuals which can block it, but there will probably be like a big referendum which is going to decide whether it can be built or not.
But we have to make a general consensus about it. That's absolutely true. We just finished all the questions.
Yeah, I was going to say, I didn't see any other questions. And I do know that some of them have to move to the next thing for their day. But thank you all so much for doing this virtual visit for us. I know that there's a recording, and I'll make sure and post it on our website so that they can link to it and get that information again. So again, thank you for taking time out of your day to do this and provide such an awesome tour for us. Really, really appreciate it.
Thank you very much.
Great.
Thank you. Have a nice day. Bye-bye.
Bye-bye.
Thank you. Bye.
Have a good day, everyone.
Bye.